Okay, so before we jump into lecture, the tests are almost graded. I hopefully will be able to finish them today. So after we talk about the experiment during the lab part for the synchronous lab part, I'll keep grading. Uh, Hopefully I'll finish them. If not, I'll definitely finish them tomorrow though. So those will be available soon. The other thing that will be available soon, I'm going to have an exam reflection option for you guys. So I don't know if you've had any other teachers that have done that in general, or especially since we've been digital. It's essentially like doing exam correction. So, correcting your wrong answers, getting some points back. But it has also like an introspective portion to it, essentially like thinking about what did you do to prepare for the test? What grade did you expect to get? Did you get that grade? What do you think you should change next time you study, or do you think you should change anything? So essentially kind of evaluating how you prepared for the test, how you did on the test, looking at the ones that you got wrong and seeing if there was any type of pattern, in terms of like maybe there was one concept that just didn't stick well, or maybe one concept that you just didn't get a chance to study that much and it popped up in a few places. So, that kind of idea. I have done stuff like that in the past, but not exactly like that. So I need to put together a document. So I have some from other teachers and just some I found online. So I'm going to kind of mush them together to come up with something that I like and post that for you guys. So you'll be able to do it for test number 2 and or test number 3. So you can do it for both, for neither one if you don't want to, for one of them. I'm not doing it for test number 1 because I posted the answer key for that already. So I don't want you just to like copy down answers, because that's not really the point of this. The point is to actually learn, because hopefully by now you've definitely seen that we don't get to forget past chapters. It all just builds. So even next semester, we'll be referring to SN2 mechanisms. We'll be referring to hydrogenation reactions. And so when I talk about flashcards and when I talk about reaction notebooks, it's because we will need that information. We'll need it for this upcoming test. You'll need it for a test you take in November. It just builds on each other. So I want you to take some time to go back and look at the stuff that you may have missed and kind of work on it. You can definitely work on it together though. So I would encourage that. And I'll talk to Justin and Emma about it too. Short story, Justin, because I know you popped in, but I'm going to have them do some kind of like little test corrections for test number 2 and or test number 3 if they're up for it. So I'll send you and Emma the info as well. But yeah, I'm going to get that up by the end of the week. So after I finish grading the test, that will be the next thing on my list, is to get the information in the document for that. Okay, chapter 9. Okay, so we have a couple reactions left in this chapter. And so we're going to talk about some of the reactions and do some practice box problems. And then the last section in this chapter is multi-step synthesis reaction. So we'll spend a little bit of time there because I have three practice problems for that. And, they each take a little bit of time. So we'll spend some time in that section. So we are starting with reaction 6 and reaction 7. And they are very similar to each other. And they're also very similar to reactions we saw in chapter 8. So in chapter 8, we took an alkene and reacted it with a halogen, X2, so Br2 or Cl2, and we added 2 chlorines or 2 bromines to each of those vinylic carbons. So here's what we're doing in our alkyne chapter. Reaction number 6 is just using 1 mole of the halogen. So we're starting with our alkyne. we're reacting it with one equivalent of X2. So notice it tells us right here, the X can be bromine or chlorine. So no fluorine, no iodine. Remember, fluorine is too reactive, a little bit explosive. Iodine is too unreactive, just too slow. So we stick to the middle ones. One equivalent of X2. So a couple other ways that you might see this written out. One, and then equivalent abbreviated as equivalent abbreviated as EQ, so one equivalent. You might also just see it written as 1 mole of X2. Essentially, we're emphasizing the fact that we only want one of these. So any of those ways would be correct. Any of them would work. Underneath that arrow, we have CCl4. This is carbon tetrachloride. This is the solvent. So we've talked about solvents before. They're important because they provide us a solution to react in, but they're not part of the reaction at all. So it is an important component, even if we don't see it show up in the product. What we're going to do is we're going to add a halogen to each of those alkyne carbons. And we're using the pi electrons to help create those bonds. So one pi bond goes away. So we go from having a triple bond down to just the double bond. And stereochemistry-wise, we're going to get two products. This reaction can go through the anti and the syn addition. So when we talk about, the regio and the stereochemistry, here's the stereo part. It does both. It can do the anti addition and the syn addition. So let's give these some labels. The one that's labeled as our major product, we know that this is trans. We can see that the two halogens are opposites, are trans to one another. This would be from the anti addition. And then the one that is our mainer, not our mainer product. I think I was trying to say major and minor at the same time. No, that's not a word. The one that is our minor product is the cis product, and it comes from the syn addition. And so there's our stereochemistry. Regiochemistry, nothing to talk about because we're adding the same atom. We're adding two of the same halogens to each of those carbons. So we don't need to talk about which carbon gets which one. It's the same thing. So we've done regio, we've done stereo. No mechanisms for either one of these. So again, this doesn't quite fit into those patterns that we've talked about and the patterns that we developed in chapter 8. So we don't talk about it. There's actually very few mechanisms in this chapter that we will discuss. I think we've only talked about one so far, and we only have one more to talk about. So very light on the mechanisms in this chapter. So we've done regio, we've done stereo, no mechanisms. So let's look at the second reaction on this slide then. The second reaction is the same thing twice. So this time we're going to react our alkyne with excess halogen. So again, we're using X2. That X can be a chlorine or a bromine. And it's written on the line here as excess, but we could write that as literally the letters X and S. And I'm just going to use bromine so I don't have lots of X's. So we could write it as XS Br2. We could write it as 2 equivalents of Br2, 2 moles of Br2. And then you might also see it written as Br2 times 2. Probably not as common, but it would definitely work. The excess, just the letters X and S, is definitely the most common. It's the shortest. It's the quickest to write. We like our abbreviations, so that's probably the one you'll see the most. Same solvent, carbon tetrachloride. Obviously starting with an alkyne there. Both of these are shown with a terminal, but no, sorry, let me say that again. Both of these are shown with an internal alkyne, but they would work the exact same if we had a terminal alkyne. So either or, it wouldn't matter. When we do this reaction, we're going to add our halogen, whether it's bromine or chlorine, twice. So each of those alkyne carbons is going to get 2 halogens. So we end up with this thing on the end here. So 4 halogens attached to those 2 carbons, so 2 each. I didn't give the top one a name, so I need to do that as well. But this is a vicinal geminal tetrahalide. So tetrahalide, because there's 4 of them, tetra. Vicinal geminal, because there's 2 on one carbon and 2 on the other carbon, and then those groups of 2 are vicinal to each other. And then the ones above it, let's give those a label also. These would be vicinal vanillic dihalides. So dihalides, because there's 2 halogens. Vicinal, saying that they are on next door neighbor carbons. And vanillic, those next door neighbor carbons are carbons that are part of an alkene. So labels that just kind of help us talk about them, give us reminders of what we're making, kind of connecting the language to the structure there. I'm looking at my notes here. 6, 7. Any questions about either one of those? So for that second one, in terms of stereochemistry, regiochemistry, regio, we're giving the same atoms to each of those carbons. They're each getting either 2 chlorines or 2 bromines, so no regiochemistry to talk about. Stereochemistry, we're adding 2 halogens to each carbon, so we're definitely not going to create any stereocenters because they're going to have 2 of the same halogens attached to them, so they can't be stereocenters. So there's really not any stereo or regiochemistry to talk about. Okay, so this takes us to reaction number 8 then. Number 8 is ozonolysis. So again, we've seen this reaction with an alkene. And when we reacted it with an alkene, we cut that alkene in half and we created ketones and aldehydes. In our alkyne reaction, we're still going to create carbonyls, carbon-oxygen double bonds, but a different specific carbonyl. And we have 2 different versions. The internal alkyne is at the top. So this is one of the few times we actually split the reaction. Well, maybe split's not the right word. One of the few times where we look at how the internal and the terminal react separately, because they do produce slightly different products. So when we start with that internal alkyne, we're reacting it with ozone. So O3, there's our water in the second step. That's also a little bit different from when we reacted it with alkenes, the second step is. What we're going to do is we're going to cut that triple bond in half, right down the middle, and each half is going to become a carboxylic acid. So we're going to make 2 carboxylic acids. Now the way that this one is labeled is that we have R1 on one side of our alkyne, and we have R2 on the other side of our alkyne. If this is a symmetrical alkyne, then we will make 1 carboxylic acid, because when we split it in half, if both sides are the same, we're just making the same carboxylic acid on each side. If it's asymmetrical though, then we're going to make 2 different carboxylic acids. So just kind of depends on if those carbon groups are symmetrical or not. When we do this with an internal alkyne, because we're making potentially two different carboxylic acids, if it's asymmetrical, doing this in a lab setting, so doing it in real life, can be really difficult because usually when you're done, you would want to just have one product. So that means that we would have to separate those 2. We've talked about different ways of separating things in lab, but 2 carboxylic acids are going to have very similar polarities. So we did our whole lab where we looked at whether things were miscible or soluble. These are going to be in the same layer, so they wouldn't be able to be separated that way. They're also going to have very similar boiling points because they have similar functional groups. So separating them by distillation would also be difficult. So long story short, doing this lab in real life is going to be most commonly done with a symmetrical alkyne so that we only get one product, or with a terminal alkyne. So let's look at the terminal one down here. So here's our terminal alkyne. I did not spell that right. Same reagents, ozone and water. We're still going to cut that triple bond in half. And one side is going to make our carboxylic acid. The other side is going to make CO2 gas. So we're going to make one carboxylic acid and the other side's going to make carbon dioxide gas. Now, why this is beneficial to doing this in the lab is because CO2 gas is just going to bubble away. So if that's our side product, our extra product, we wouldn't have to worry about actually separating anything because it's just going to separate itself. It's just going to bubble away. So this would be a reaction that would actually bubble or fizz. And that bubbling is that CO2 being produced and that CO2 leaving the solution. So one thing I do want to point out, I'm going to draw one reaction up here at the top. I try to remind everybody to count their carbons often. And I want to talk about counting carbons for this reaction. So if we are doing an ozonolysis reaction with a terminal alkyne, we have to remember that one of those carbons is getting kicked off. It's turning into that CO2. So I'm going to count my carbon chain. I have 7 carbons. Carbons 1 through 6 are going to become a carboxylic acid. And then carbon 7 is that CO2. So I bring this up because we want to make sure that our answers have the correct number of carbons in them. And this is a time where we want to count our carbons, but also we have to understand that one of those carbons is breaking off and turning into CO2. If this was our answer for a test, we would actually only need to show the carboxylic acid. It's not completely necessary to show the CO2. Because it's not the product we care about, because it's just bubbling away, we would not consider it to be one of our final products or one of the products that we care about. Questions about that ozonolysis reaction at all? Okay, one more reaction then. And I think that this last reaction that we're talking about is probably the most important reaction we've looked at so far. And the reason I say that is because it's an alkylation reaction. So what that means is that we are creating carbon-carbon bonds. We're adding an alkyl group onto our chain. We have very few reactions that create carbon-carbon bonds. Most of the reactions we've talked about create carbon-oxygen, carbon-halogen, carbon-nitrogen bonds, or break those bonds. But making a carbon-carbon bond is kind of difficult to do because carbons by themselves are not very reactive. We have to force them to be reactive by turning them into carbocations or adding an electronegative atom to them so they become partially positive. By themselves, though, they're happy and stable. So we have all these reactions that allow us to change the functional group. This is one of our few reactions that allows us to change the carbon skeleton. So here's our reaction. We're going to start with a terminal alkyne, and it does have to be terminal. We are going to react it with sodium amide. So we talked about this reagent at the beginning of the chapter. It's a very strong base. So we talked about that we can use this as our strong base for this reaction because the conjugate acid that it produces is weaker than the alkyne hydrogen's acidity level. In the second step, we're going to react it with an alkyl halide. So the one that's shown here, we're looking at ethyl iodide. So we just need Rx, we need an alkyl halide. So it doesn't have to be iodine. Bromine or chlorine would work as well. The R group has to be a methyl group or a primary group. So where that halogen is attached, either just needs to be a methyl group or it needs to be attached to a primary carbon. This doesn't work with secondary or tertiary. They're just too bulky. There's too much steric hindrance. What we're going to produce is an internal alkyne. So name-wise, it doesn't seem like we're doing a whole lot here. Let's see if I can spell some words right. Let's try that again. So let me number some carbons and show you where this came from. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7. 6, 7. So the new bond that is being formed, this bond right here, that's our new bond. This is a new bond between the terminal alkyne carbon and the alkyl halide carbon. So we've created a new bond between those two. We're going to look at the mechanism for this one on the next slide. So this is one of the very few mechanisms you need to know for this chapter, but it's on the next slide. If we start with ethyne, so on the bottom here, we're specifically starting with ethyne. So that means we now have two terminal sides to work with. We can do this reaction twice. We can do it back to back. So in this case, we're going to react it with our sodium amide and an R group. And then we can react it again, sodium amide and an R group. And we can have two different R groups on either side. So we can create an internal alkyne that is asymmetrical. So here's what's nice about this reaction. I said it's the most powerful reaction that we've learned so far. First, it is creating a carbon-carbon bond. So it's changing that carbon skeleton, which we have very few reactions that let us do. The second thing is that we still have the triple bond. And a lot of times when we do a reaction, whatever we used to do that reaction, if we were using the pi electrons to make new bonds, those reactive sites, those reactive atoms go away. They're not reactive anymore. But the way this reaction works, we still get to keep that triple bond. So that means all the other reactions we learned in this chapter, we could now do. We could go through a series of reactions to create a ketone, to do the ozonolysis and make carboxylic acids. We have all these other reactions that we could pair up with this and make something bigger with a different functional group. So very powerful reaction. And as we do practice problems, especially with the multi-step synthesis ones, you will see ethyne as a starting material a lot because we can add on whenever we want to each side and then continue to do reactions with it. Questions about this reaction at all? Okay, let's look at the mechanism for it. It's actually a pretty short mechanism. It's just this is the whole thing. And there's nothing weird. We're starting with a proton transfer. So there's our amide, our NH2 minus. It's our base. It's going to take that hydrogen off of our terminal carbon, and then the electrons go onto that carbon. So this is just a proton transfer. And we're going to create our carbanion. So specifically because it's a triple bond, it's called an alkynide ion. You're not going to hear that word very often, though. More generically, it's a carbanion because it's a carbon with a negative charge. In that second step, we're going to go from the carbon right onto our alkyl group, and then those electrons are going onto the halogen. So the first arrow, this arrow right here, what type of mechanism pattern is that? We have proton transfer, carbocation rearrangement, loss of a leaving group, nucleophilic attack. Any thoughts? Oh, I see in the chat. Perfect. In the chat, we got nucleophilic attack. It's exactly what's going on here. And then what about our other arrow? So the one that's going from the bond onto our halogen. What type of step is that one? Ooh, sorry if you heard that. That was my neck. It is the loss of a leaving group. Thank you. All right. We've seen this exact mechanism before. When we do a nucleophilic attack at the exact same time that we're doing the loss of a leaving group, what's the name of that reaction? Do you remember, or does it look familiar at all? Good. That's an SN2 reaction right there. So we normally, when we talked about SN2 reactions, we focused more on the substrate, on that R group. But this time we're focusing more on the nucleophile because that's the part that we care about. That's our alkyne. It's the same thing though. And this is what happens in organic chemistry a lot. We talked about 4 mechanism patterns. There's a couple outside of that, and we'll look at a couple of those. But for the most part, we only see those 4. So they just get repackaged with some different colors, but it's the same thing inside that packaging. It's still an SN2 reaction. So we'll continue to see SN2 and E2 reactions often. SN1 and E1 not as often, but SN2 and E2 definitely pop up time and time again. This is the whole reaction though. We take that hydrogen off to create a good nucleophile. And then we do a nucleophilic attack with that loss of a leaving group, and we make our new internal alkyne. Any questions about the mechanism? Okay, let's do some boxes then. Let me draw some stuff out for us. Let's see. I ran out of space this morning. I'm trying to decide how to space this out a little better. Oh, that's the wrong one. No wonder why I was confused. Okay. Let's start right here in the middle. Okay, all product boxes this time. But we have 5 different boxes there. Let me turn on our screen annotation. Okay, so the screen annotation is on. Please feel free to fill in one of our products into the boxes, and then we'll talk about them. I'll add in some reaction numbers. Looking good so far. I'm moving some zoom controls here so I can write on my screen. So I was going to label these with reaction number. So if you want to go back and look at stuff. So this is number 8 up here. And it is correct. It looks great. I'm going to number some carbons so we can see where everything came from. So I'm going to do 1, 2, 3, 4, and 5. And then on my original structure, 1, 2, 3, 4, and 5. So we cut that triple bond in half. That terminal carbon, carbon number 5, became CO2, and carbons 1 through 4 became carboxylic acid. So it looks great. I'm going to use those same numbers as we look at the other stuff. Get my zoom controls back out of the way again. Okay, and then let's see. The purple structure over there is the one we just did, which was number 9. Oh, and it looks good. So this one was a little tricky. Let me show you why it's a little tricky. So we have 1, 2, 3, 4, 5. What's really common to do, incorrect, but common, is to say, okay, I'm going to make my bond go right there. There's my new structure. But get my little eraser. It's not what we want. We want to form the bond to this carbon. So there's 6, 7, 8, 6, 7, 8. The bond between our alkyne and our alkyl halide has to connect where the halogen was. That halogen's our leaving group, so that's where we want to connect it. So don't resist that urge to just draw the line between them. So this looks great. Okay, I'm going to go left to right. So we'll start, oh, as the green one looks like it's just getting finished up there. So that was number 6. And we'll do some numbering. 1, 2, 3, 4, 5. Looks great. 3, 4, 5. So we've added our chlorine on once to each carbon. We have it in the trans version. We have it in the cis version. We're going to get both of, oh, I labeled those backwards, didn't I? I looked up at my shared screen and realized they were backwards. Let's try that again. We'll get the trans version. We'll get the cis version. The trans is our major product. That's just a sterics thing. The 2 chlorines are farther away from each other, so it's happier. But looks great. Next one over. So this one's very similar to the previous one, but 2 times. So we're going to do number 7. So we have 1, 2, 3, 4, 5. So carbons 4 and 5, those alkyne carbons, get 2 bromines each. And we know that because in this one it said excess. So that means we're going to essentially add bromines until we can't add bromines anymore. And the one we just did said 1 equivalent. So that's the big difference there, is in the reagents, it's telling us how much we're going to add. All right, last one. So this is also ozonolysis. So this is also number 8. But in this one, we're building off of the structure we already drew. So we're going to cut our purple structure up there in half. So we have 1, 2, 3, 4. And then on the other side, 5, 6, 7, 8, with that methyl group coming off of carbon number 7. So that looks good as well. And so I have ozone on there twice. Just a reminder that we get CO2 if we're making our, or if we're starting with our terminal, and then we get the 2 carboxylic acids if we're starting with our internal. Could you explain reaction number 9 again, please? Yeah, so in reaction number 9, we're going to form a new bond between carbon number 5, so that carbon on the end, and the carbon that's attached to our halogen. And so the NaNH2, moving my little controls out of the way here, after that first step, we end up with that carbanion. And then we're going to form our new bond right there as our iodine takes off. So what I was emphasizing is that we want to make sure that the new bond is happening where the halogen was attached. So our new bond that's taking place, let's see, that's purple, so we'll do red. This is our new bond right here. So between carbons 5 and 6, that's where we connected those 2 groups together. Any other questions about these reactions? So obviously I like to number my carbons, I like to number my structures. I think there's just as many numbers on this page as there are molecules. But it's a really easy way to check your work. It's a really easy way to make sure you didn't magically lose or gain a carbon. I've said this before, I'm going to say it again right now. There's no right or wrong way to number your carbons because you're just checking to make sure that you have everybody. I will often number mine in a specific way to make sure that things line up, meaning right here to make sure that we went from 5 to 6 to 7 to 8 instead of going from 5 to 8 to 7 to 6. But if we did, it doesn't matter because we're just marking them to say, okay, here's carbons 1 through 5, here's carbons 6 through 8. We know they're coming together. It doesn't have to be numbered in order. So we just want to make sure nobody gets left behind. We didn't pick up any stray carbons along the way. Okay, before I clear out the screen here, any questions? Just like that, it's gone. How sad. All right, last section. Last section is looking at multi-step synthesis reactions. And the pattern within this chapter was the same that we saw in chapter 8. It's the same we're going to see in most chapters. We start with some kind of background stuff, physical properties, maybe some polarity, some acidity, just kind of some background information on the functional group, usually some nomenclature, all the reactions, that's the bulk of the chapter. And then at the end, we talk about multi-step synthesis. Multi-step synthesis is usually incorporating reactions from previous chapters as well as the current chapter. And because we now have a few chapters under our belts, we're also looking at what questions to ask to approach these types of problems. So our book kind of takes a two-sided approach. The first one is asking, does the carbon skeleton change? So this could be kind of looking at two different things. The bottom picture on this slide is showing us going from a triple to a single. I skipped double in there. Going from a triple to a double to a single bond, or reverse. So that's one way that a carbon skeleton could change. The other way is by either gaining carbons or losing carbons. And we really only know two ways to do that. We can gain carbons if we have our terminal alkyne and we do our alkylation reaction. So the last reaction we learned, reaction number 9. We can lose carbons. Now this isn't really losing carbons, but it is going to be cutting our chain in half when we do ozonolysis reactions. So whether we have a long chain and we're cutting it in half to make 2 carboxylic acids, or if we started with an alkene, 2 aldehydes or ketones, or if we have a terminal alkyne and we're just cutting off that last carbon and creating CO2, we are removing a carbon from that chain. So these two reactions, this was number 8, these two reactions will change the number of carbons in our chain. They're the only two we have that will do that right now. So on the bottom, we've learned most of these reactions, but we know that we can go from a triple bond down to a double bond using hydrogen with Lindlar's catalyst or sodium with ammonia. So hydrogen with Lindlar's catalyst, that will give us our Cis Alkene. Sodium and ammonia will give us our trans alkene. And then we can go from our alkene down to our alkane with hydrogen and a catalyst. So it does say platinum on there. We also talked about palladium, talked about nickel. We also know that we could just do this in one step, going from the alkyne to the alkane with hydrogen and that platinum as well. We can go the reverse direction. Now notice that the first one, going from an alkane to an alkene, we haven't quite learned yet. We'll get there next week, so coming soon. But we do know how to go from an alkene to an alkyne. Now we didn't learn that reaction directly, but look at our reagents. We're going to react our alkene with Br2. So that means we're going to add a bromine to each carbon. Oh, I need to grab my little fan. My tablet is getting slow on me, which means it's getting hot. Somehow it just got hot in my apartment in the last like 15 minutes. Okay. So if we add Br2, we're halogenating, we're brominating each of those carbons. And then in the second and third steps, we're adding NaNH2 and water. This was, I think, our first reaction in this chapter. It sure was. So this is a way to create an alkyne. We're essentially doing two elimination reactions back to back. And for this one, we actually don't need the water. Let me get rid of the water there. Remember, the water is necessary if we're making a terminal alkyne, because we need to make sure that the hydrogen on that end carbon is still in place so that the base didn't remove it. So we didn't learn these as one package deal, but we can definitely combine them together to go from an alkene to an alkyne. So that shows us how to do all of our carbon skeleton changes. The other question on this slide then says, do the functional groups change? So this is what the bulk of our reactions have been. In chapter 7, we learned how to take a leaving group off and replace it with a new nucleophile. The things that can be nucleophiles are huge. There's a huge list, anything negative pretty much. In chapter 8, we learned how to make ketones, and we learned how to make aldehydes and diols and alcohols and halohydrins. And then in this chapter, carboxylic acids and ketones and all kinds of aldehyde or halogen groups. So we have a huge list of potential functional groups that we can make. In terms of what we can start with, we know how to start with something that has a leaving group. We know how to start with alkenes, and we know how to start with alkynes, because those are the chapters we've covered so far. So this is essentially the approach we want to take. And to answer those questions, we take a little inventory at the start of our reaction for the reactant and the product. So we're going to do a couple practice problems. Let me move my little video out of the way here. Okay, so here's our first one. We're going to start with ethyne, and we're going to make a 6-carbon chained aldehyde. So to answer both of those questions, does the carbon skeleton change? Do the functional groups change? We can definitely see some differences, but we're just going to take a little inventory. On our reactant, we only have 2 carbons, and we have a triple bond. On our product side, we have 1, 2, 3, 4, 5, 6. We have 6 carbons, and we have an aldehyde. How can we change our 2-carbon chain into a 6-carbon chain? Yeah, reaction number 9. So reaction number 9, our alkylation reaction. So we're going to react this with NaNH2. And I need to add 4 carbons. So I'm going to draw it out like this. I'm going to put an iodine there. I could have also written it as butyl. So butyl iodide like that. One, two, three, four. All right, I'm going to do some carbon counting, carbon labeling here. 1, 2, 1, 2, 3, 4, 5, 6, 3, 4, 5, 6. I numbered my alkyne carbons as 1 and 2 because I wanted that carbon right there, the one where the aldehyde's attached, to be one of the alkyne carbons. I wanted to have that consistency. I know that these carbons over here aren't going through any reactions. They're not reactive carbons. So my reactive carbons, my alkyne carbons, need to be where that functional group is getting added on. All right, do we know how to turn a alkyne into an aldehyde? Yes, we do. So this is reaction number, I was trying to find it, number 5. So this is one of our boring reactions. So as we saw boron-based reactions in chapter 8 as well. So essentially it's adding an oxygen, anti-Markovnikov. So we're adding an oxygen to that end carbon. And for this reaction, we are going to either use diethyl boring or 9-BBN, which is the one I like to use, and some hydrogen peroxide and hydroxide. And that's it. This is a 2-step reaction. So it looks like there's a lot of stuff that's changing and happening, but really we only have to do 2 things. We add on the carbons, we create the aldehyde. So a couple things to talk about with this reaction though before we move on. When we are approaching a problem like this, we know we have to change the carbon skeleton. We know we have to change the functional group. What order do we do these 2 things in? Sometimes it matters, sometimes it doesn't. I know that's a horrible answer, but honestly, it's the truth. And what I mean by that is if in this reaction, if we started with our 9-BBN reaction, if we did this, we did our 9-BBN, and we just kind of thought, well, I'll do my aldehyde first, and then I'll add on my carbons, we would make an aldehyde. But then we couldn't add our alkyl group because the alkyl group has to have a terminal alkyne. So in this reaction, the order that we did those 2 steps in definitely matters. We have to have the right type of reactant for our reagent. So if we do need to add on alkyl groups, if we need to make that chain longer, that's almost always going to be our first step because we have to have a terminal alkyne. So we don't want to mess that up. We need to use that. But after we add that alkyl group, we still have that triple bond. So that triple bond could then go through one of our other reactions. We could turn it into, for example, the aldehyde here. Any other questions about this one? Okay, let's look at one more then. Okay, so we're starting with ethyne again. You will see that a lot as a starting point. So 2 carbons with a triple bond. We're going to make 1, 2, 3, 5 carbon chain with dibromides. And remember, there's a couple different ways to approach these problems. We could approach them going in a front direction like we did with the last one. We could also approach them going kind of a backwards direction, which is called a retrosynthesis. So for example, for this one, we know how to add 2 bromines to a chain. And specifically, these 2 bromines are both on wedges. But if you remember back when we learned about adding 2 bromines in chapter 8, they have an anti addition. So in order to get them to look like that, we would need to add them to a cis double bond. Because then when they add, let's put it right here, we would have one on a wedge and one on a dash. And so then after it rotates around, it would look like this. But we would need Br2, put some solvent in there. So this is a chapter 8 reaction. So we might recognize that to start with. We might say, okay, I know how to add 2 bromines next to each other. I know I can get that if I start with an alkene. And so that kind of takes care of one thing. That takes care of the functional group that we need to have. And so now we have a new goal. Now we have, well, I have my alkyne. How do I turn that into this cis alkene? What should we do first? Yeah, I think we should add carbon chains as well. So I'm going to do some numbering here so we can figure out how many carbons we need to add. I'm going to just number what I have, 1, 2, 3, 4, 5. And number our product up here as well, just make sure we're in the right chain there. Now, if I want my numbers to match with my reactant, what numbers should I give my alkyne carbons? What numbers do they represent in that product or in that green structure? Not sure if I asked that right. Yeah, they are 2 and 3. So if you didn't quite understand my question, let me explain the answer, and that will hopefully help you understand what I was trying to get at. What I mean by that is our 2 original carbons, our alkyne carbons, are part of both of these structures. And so my question was trying to get at which 2 carbons are the original alkyne carbons. And because they are the ones that need to remain reactive, they are the ones that are the double bonded carbons in our green structure, or the ones with the bromines in our final structure. So what this tells me is that I need to add a methyl group to one side, and I need to add an ethyl group to the other side. So we need to add 3 carbons altogether, because we're starting with 2 carbons and we're making a 5 carbon chain. But we don't just want to add a 3 carbon chain. If we did this, NH2, 1, 2, 3, we would then have our double bond here, our 2 bromines there. They'd be at the 2 end positions, and that's not what we're trying to create. So we do want to add on those carbon groups separately. So I'm going to, and in this case, the order does not matter. I'm going to add the methyl first just because I numbered it carbon number 1. No other reason. Add some numbers back in here. There's 1, 1, 2, 3. And then I'm going to add in the ethyl. So NaNH2, my ethyl group. I'm putting this kind of weirdly on the bottom because I know I'm going to need to do one more step. So this is carbons. Whoops. I want to number it in the right way. That's carbon 4. That's carbon 5. All right, so that means we have 1 step left. We need to go from our alkyne to a cis alkene. So we learned how to go from an alkyne to an alkene 2 different ways. One was cis, one was trans. Do you remember which set of reagents we used to get to the cis alkene? So this one is hydrogen with Lindlar's catalyst. So this ended up being a 4-step reaction. On the test, what I have written down in green would be your answer. The way a question like this is asked on the test, so this was like the last question on your most recent test, it will say something like, provide a set of reagents to convert the given reactant into the given product. So you can definitely draw out those intermediate products. And when I say intermediate products, I'm talking about this and this and this. And I'm referring to them as intermediate products because they are the products of those reactions, but it's not the final product that we're trying to create. So what's presented in green definitely is an acceptable, good answer. Another way to write out your answer is to put all of those reagents on that top arrow together. So we could say, oh, nope, that's not what we're going to say. We could say step 1, NaNH2, step 2, CH3I, step 3, NaNH2, step 4, ethyl iodide, step 5, hydrogen with Lindlar, and step 6, bromine and some solvent. If you put that orange box of information on the test, and that was your answer, you would also get full credit. Now here's the catch. If you do it that way with the orange box, you just put the set of reagents, you don't draw any of the intermediate products, and all of your reagents are good, they're all correct, you're going to get full credit. You won't lose any points. If you do it the orange way, you have all your sets of reagents, but something's not quite right. You, instead of NaNH2, you put Na and NH3. Just, mistake. It's one number difference. It actually is going to mean something very different, even though it's just one number difference. If that's all you write, I'm not going to know that that was a typo. I'm going to think that you meant to add sodium and ammonia. And so by showing me your structures after each step, I can see that you meant, oh, they meant NaNH2. That's just a tiny typo. Instead of that set of reagents isn't going to help them out here. So it will help me give you partial credit if you draw in those intermediate products, if something goes a little bit amiss. And so you might even see that on your most recent test that I kind of fill things in or draw things out as I'm trying to figure out what you might have meant or try to figure out what your reagents would do. So just kind of a little side note there on how to present your answer, how to get the maximum number of points. Any questions about this reaction or multi-step problems in general? Okay, let's do one more. That was a weird bond. Let me redraw that bond. That's a little better. All right, we're starting with a 3-carbon chain, and we have a triple bond. We're ending with 1, 2, 3, 4, 5, 6. We're ending with a 6-carbon chain. And that little functional group right there is an epoxide. So it is an ether. You could also call it that. It's just a specific type of ether. It's a cyclic ether. So we got to add some carbons on. We got to get rid of a triple bond. We got to make an epoxide. Do we remember how to make an epoxide? We've only seen it once. It was a chapter 8 reaction. Yes, MCPBA, perfect. And so I asked that because it's such a specific functional group that I think this is a very good time to utilize our retrosynthesis approach. Because we have to have an alkene at that location. We react it with MCPBA and we can get our epoxide. So if that doesn't quite ring a bell to you, when we did this in chapter 8, we reacted it with MCPBA, or really any peroxy acid, but MCPBA is the most common one in the first step. In the second step, we used acid and water, and it created our diols. There were a couple times when we looked at this, though, where we didn't use the water and the acid, and we just kept it as the epoxide. So MCPBA will get us to that epoxide. So now we have to worry about going from our alkyne to our alkene, and we know how to do that. So let's number some carbons here. I'm going to number right here 1, 2, 3, and the reason I'm numbering those 3 is because 1, 2, 3. There's a methyl on the end of that chain attached to that alkene carbon. There's a methyl right here, so I know that those 2 methyl groups are the same. So that means that I need to add on carbons 4, 5, and 6. So we know how to do this. We've done it in all of our practice ones so far. This is probably going to be the reaction you use the most in multi-step synthesis, but we're going to do NaNH2, and we need to add on 3 carbons. So here are carbons 4, 5, and 6. So we have 1, 2, 3, our original alkyne carbons, and now carbons 4, 5, 6 added on. Now there's not really any chemistry, or not chemistry, there's not really any stereochemistry shown in our final product. There's not dashes or wedges. I did draw my alkene as trans, so let's use the reagents for that because we've already used the ones for cis. Do you remember what reagents we need to use to go from an alkyne to a transalkene? So we need to use sodium metal. Good, I do see it in the chat over there, perfect. So sodium metal and liquid ammonia. And so that will give us the transalkene. We used, I'm going to go back one slide for a second here. Right here, we used hydrogen and Lindlar's catalyst, which gave us the cis alkene. So using those to get to the stereochemistry you need can help you out a lot as well. In this case, we didn't really have any defined stereochemistry, so we could have used either one. But that's it. There's our 3-step reaction. So it allowed us to make that chain bigger, get rid of our triple bond, and put in that new functional group that we needed. Questions about that one at all? Okay. If these last 3 problems had you lost, little lost or big lost, definitely need to practice with them. If you haven't made a reaction notebook or reaction flashcards, start back at chapter 7, use that as some review, and start working on having those summary pages or notebook or flashcards, whatever it is that helps you out. Definitely do the practice problems in the book. And then the last thing, chapter 11. So I know we're currently in chapter 9, but chapter 11 is kind of a weird chapter in this book. So we're going to start chapter 10 next week. Chapter 11 is literally just called synthesis. And I don't even lecture on it in class because literally we just use it in every chapter. We're, doing synthesis right now. But chapter 11 goes through how to approach these kinds of problems. And there's a lot of really good examples. In fact, the first 2 problems within the chapter, like the conceptual checkpoint problems, are the reaction maps from chapter 8 and chapter 9. So just the alkene in the middle and all the things it can turn into, and the alkyne in the middle and all the things it can turn into. So really good, just do you have your reagents memorized questions? And then it has a lot of practice problems to help you figure out how to do these multiple stepped problems and how to reason them out. So looking at them from a forward, looking at them retrosynthetically, thinking about regiochemistry, thinking about stereochemistry, has a lot of really good practice problems in there using the reactions from our chapter. Looking for practice problems for stuff like this online can be a little bit tricky because different books have different reactions that they cover. So we can't cover every reaction in organic chemistry. And another thing that can be tricky about it is finding problems that are at the same level. What I mean by that is you might find some good practice problems, but they might include reactions from chapter 13. And so it can be a little bit difficult. So what's nice about chapter 11 is that it has the appropriate reactions and the appropriate level. So really good practice problems in there. And then of course, just within our own chapter that we're currently in. Okay, any multi-step synthesis questions or chapter 9 questions at all? Okay, that is it for chapter 9. So we have about 10 minutes left, so I'll hang out and see if there's any questions. But if not, I will see you in lab for those of you that have synchronous lab. And if not, I'll see you on Monday if you don't come check out office hours with me. But that is it. So thanks for hanging out today, guys.
From a creation of problem standpoint, these chapters actually get kind of nice because the multi-step synthesis, you can just randomly pick and choose reactions.
Yeah, it's funny because in the beginning they're hard to make because there's just not enough reactions. And in the end, it actually becomes kind of hard because there's so many reactions that it's hard to force students to do it in 3 or 4 steps because they can always find a way to just do it in like 2 steps because they know too much at that point.
Yeah.
So we're in a good area for these types of practice problems.
Nah, I was bummed on Monday because I got an email back from Fullerton and I didn't get into the research thing.
Oh, I'm sorry.
It's a bummer, but what can you do?
Yeah.
They said that if somebody doesn't accept or they drop out by like May 17th, they may get back to me, but yeah, I'm not gonna rest my hopes on that.
Yeah, no. I mean, something that would be nice if it happened, but yeah.
No, I was confused in another class I'm in at IVC because the teacher was offering this extra credit by going through something called like talent ed, and it's really focused on like trying to find a career, finding costs of living in this area, and like trying to reason out like, all right, what's your actual game plan out of all of this? So it was kind of cool, but then I got really confused because there was one section where it's just like, all right, find a company and then find how much they make, what the names of their titles are, and like all these other details that are related to employment. But when you look at engineering firms and stuff like that online and you look at their site, they don't have that information. All of their information is dedicated to they sell a product or a service. Here's the product and service they offer. Contact this number to inquire about prices. And everything else is like, if you want a job there, then you'd have to like either find it on Indeed or some other site or like directly contact them.
Have you ever used the website Glassdoor?
Mm-mm.
So Glassdoor is essentially like a place for employees, like employees that have left a company to like leave reviews for a company, but it will often have salaries on there. So it is also a way, like if you were, asking for a promotion or even just starting a new job, it's a place to look at what other people make that are doing the same type of job. So that might be a place to find salaries.
Interesting. Nah, I was only like thrown off because it had this like interactive map, which was kind of nifty and all. And you can click on these dots to be like, oh, there's a company here, and then here's a little blurb. Click this to go to their site. And so like half of them though just had a name, and some of them were as vague as just laboratory.